Hey guys, so I'm shooting this exam wrapper for Professor Fenton's 2211 Modern Physics class. So we did go out a test back, and so I looked at the problem I had some struggles with, and so I redid it. Looking back at it, it's actually not too complicated, so I'm going to run through it with you guys real quickly. So the problem is on the board. It says during your summer internship, you join a new bioengineering company, and you're in charge of designing small sections of cardiac tissue by connecting single cardiac cells. Cardiac cells can be approximated as cylinders, 150 microns in length and 15 microns in diameter. So part A of this question says, when you apply a force of 0.3 nanonewtons to the area of one side of the cell, you notice that the length decreases to 140 microns. What is Young's modulus for this cell? So this is pretty straightforward. We know the formula for Young's modulus to be Young's modulus equals the force applied divided by the cross-sectional area, and that's all divided by the change in length all over the initial length. So first, pretty much what we have to do is we have to solve for each of these values. So let's first start with delta L. So we know that, let's first start with L actually, because we know L is 150 microns, tells us that. And the important thing about this problem is units. That's really what this problem is testing. So we have to make sure that we know all our units, right? So L and delta L have to be in meters. So we take the 150 microns, and we know that 1 e to the negative 6 meters equals a micron, so we do that dimensional analysis. That's our L. To get our delta L, we do our initial L, which is this one, 150 microns, and we subtract what the change in length, or we subtract the final length of it, right? So we do that change in there, which is final minus initial. Sorry, not initial minus final, but final minus initial. And in that case, you know that your delta L will be 10 microns. And now, we convert that into meters as well. Then we have to get into our force and our area. So we know that our force is 0.3 nanonewtons. And so all you have to do is convert nanonewtons into newtons. When we do that, we get 3 e to the negative 10 newtons. And now here comes the hardest aspect to solve for, which is the cross-sectional area. However, it's really quite simple. So the way the cross-sectional area is, you have to find the radius of the cell. And in this case, we found out that the radius is equal to 7.5 microns, right? So then we take those 7.5 microns and we make it into meters, and then we multiply by the cross-sectional area. We find the radius, and we multiply that by pi r squared to get that entire area, that cross-sectional area of the circle. And when we do that, we get 1.767 meters squared. Then you take all these values, you plug them in, and when you do the calculation behind it, you get 24.465 Newton over meter squared as your Young's modulus. We're going to move on to part B of this problem, and so let me read it to you. It says each of these cells can be approximated as a spring with a spring stiffness of 300 nanonewtons per micron. If you construct a cable connecting 5 cells, determine the equivalent spring constant of the cable. So essentially it's saying that we're constructing them in a series. So we know the formula for series to be the spring stiffness of the series equals the spring stiffness of the spring all over the number of springs. So we had the number of springs, it's 5 because we have 5 cells, and now we have to find the stiffness of the spring. So it gives us to that as 300 nanonewtons per micron, but we can't use that because it has to be an SI unit. So we have to convert it to newtons over meters. So you take 300 nanonewtons per micron, you get rid of the microns, replace it with 1 e to the negative 6 meters, and then you take it and you get rid of the nanonewtons by multiplying it by 1 e to the negative 9 newtons. And so when you do all that, you get 0.3 newtons over meters, and so then you take that 0.3, which is your K spring, divided by 5, which is your number of springs, and you get a spring stiffness for the series of 0.06 Newton meters. Alright, so now moving on to part C of the problem. It says how many of these 5 myoside cables would you need to connect in parallel to obtain a new thick cable of cells with an overall stiffness of 600 nanonewtons per micron. So we know this is talking about parallel springs, and our formula for that is K parallel, the stiffness of the parallel springs, is equal to the number of springs times the stiffness of the spring. So what you do is you're given K parallel in nanonewtons per micron. So you have to convert that again, and when you finish it, multiplying it by the micron, or multiplying it by how many newtons you have per nanonewton, and then dividing by how many meters per micron. Once you do the similar application we did in part B, you get 0.6 newtons per meter. So that's that value. And then the K spring was solved before in part B, and we know that to be 0.06 newtons per meter, because that's what we got in part B. So you plug these numbers in, you solve for n, and when you solve for n, you get 10 springs. And so that's the answer to that question. Hey guys, so now I'm going to do part D of this problem. So if we read it, it says, you attach a small mass to the end of this newton-thick cable and suspend it from the ceiling so that it oscillates vertically under the influence of gravity. How much faster / slower would the oscillation frequency be compared to the oscillation from the same mass attached to a single 5 myocyte cable? So when looking at this problem, it's a lot of words, it seems kind of complicated. It's very, very simple actually. So when you look at it, you know it's asking for oscillation period. Like that's the idea, the oscillation frequency. So you know that formula is T equals 2 pi root over mass all over spring stiffness. So going from there, it's asking for a comparison, or I guess in this case a ratio of the oscillation period for the two numbers that we've already kind of dealt with, which are 600 nanonewtons per micron for the multiple of 5 and 60 nanonewtons per micron for the single of the 5 spring or cells in this case. So when you look at it, so what we have to do is we have to compare these two. So when we look at this formula, we see that it requires mass. And since it's a ratio, I just assume a mass. If you assume mass and keep it consistent, since it's a ratio, it won't really matter. So I assume this mass, and I go through this, and I do T equals 2 pi root 100 grams all over 600 nanonewtons per micron for that one. And then for the other one, I do T equals 2 pi root 100 grams all over 60 nanonewtons per micron. Now you might be thinking, wait, do we have to convert to SI units for the nanonewtons per micron? You actually do not have to in this case. You can, but you don't have to in this case because it's a ratio. So like I said, as long as you keep things consistent in terms of units and constant numbers, as long as it's consistent, then the ratio will still work out to be the same. So I do both of these, and then I compare the times I get. So for the one on the left here with the 600 nanonewtons per micron, I get 2.5651 seconds. And the one on the right, which is the 60 nanonewtons per micron, I get an oscillation period of 8.116 seconds. So then what you do is you essentially take one of those to be equal to 1. So let's divide this one by the lowest one. So this will be divided by 2.5651. We divide it by the same thing. And we get the ratio to be 3.162 to 1. So essentially what that's saying is that the oscillation period is 3.162 times longer in this scenario, the one with the 60 nanonewtons per micron, opposed to the other situation. So that's how you get it. That's how you compare how much faster or slower it is. Thanks for watching this problem, guys. Hopefully it helped you out if you had issues with this problem like I did. But you know, looking back at it, it was a complicated situation. But now I think I understand the problem and I'm ready to attack it on the final one. Hopefully you guys are as well. So have a good one. And once again, my name is Sagar Patani.